So intermolecular forces kind of like finishes off simple molecular bonding. Intermolecular forces talks about the forces between these little molecules. So if I consider, say, two CO2 molecules, like so, these are covalent bonds. They're very, very strong. However, if I have carbon dioxide, between these molecules are weak intermolecular forces. These are the ones I break whenever I melt or boil something. I don't break the covalent bonds because that's a chemical reaction, although when I melt dry covalent things like that. These are intermolecular forces, and there are 3 types of intermolecular force you need to know about. So, intermolecular forces, so if I put these exist between molecules. And there are 3 types. There's van der Waals, there's permanent dipole, and there's hydrogen bonding. And they get stronger. So these are the weakest, and these are the strongest of the intermolecular forces. So van der Waals forces. Van der Waals forces, they occur because if I've got, say, let's say I've got an argon atom, like so. At one moment in time, I've got electrons whizzing around my argon atom. If I was to just take a picture of it for an instant in time, I could find it's got a little dipole. The electrons are more on this side than this side. If that happens, if I've got an argon next to him, that induces a dipole into him, like so. And that gives me a very, very weak attraction, because it's due to instantaneous dipole-dipole attraction.
And that causes more, doesn't it?
Sorry?
And that causes more, so...
Yeah. Instantaneous dipole-dipole attractions. So I have an instantaneous dipole, and that induces another dipole in your neighbouring molecule. That goes for the whole sample, but it's constantly changing as we go. Very, very weak. Permanent dipole, that's when we look at our electronegativity. So if I've got, say, an HCl is permanently got a permanent dipole. So another HCl next to him is going to line up like so. So I've got a permanent attraction between those two. He's always delta negative, he is always delta plus. That's a permanent dipole-dipole attraction that occurs. And the final one, a hydrogen bonding, these occur if I've got an NH bond, an OH bond, or an FH bond. These are the 2 I need to be really think about. So, for example, if I've got water, like so, they line up. So if I draw another one, like so, that attraction between the hydrogen and the oxygen is called a hydrogen bond. Now to draw these, oxygen is always delta negative and hydrogen delta plus. The reason why this is such a strong attraction, those electrons in that bond are pretty much over here next to the oxygen because it's delta minus. So if I sat on that lone pair of electrons, I've got a direct view. What's my view going to be? Yeah, I'm basically looking at the nucleus of hydrogen because the electrons, they're over here. So I've got a direct view, and equally that proton's got a direct view of a nice lone pair of electrons.
So there's a little shield there that's just...
Yeah, they're all over here, yeah. So I've got a really strong attraction between them. So that's the strongest there. So it's a bit like permanent dipole, but because it's got hydrogen in it, which doesn't have any electrons.
It's just
Yeah,
hydrogen.
yeah. Because it's got a direct view of the proton going on. So they're the strongest, and you've got to watch out for the fact you have odd properties of water.
Like ice,
Yeah, ice floats on water, and the fact that the melting and boiling point of water are higher than we'd expect them to be, and for ammonia as well. So when you're drawing them, always put your lone pairs on. This bond angle there should be 180 degrees. It should be a straight line from there to there with your hydrogen in the middle, and put your delta plus and your delta minus on, like so.